Through most of our mathematical lives, particularly in Calculus 1 and Calculus 2, we dealt with acceleration in terms of projectile motion, and so acceleration was always constant because it was always the force of gravity. But of course, acceleration does not have to be constant. So acceleration is just the change in velocity. Now you can change velocity two ways. You can change it by changing its speed and by changing its direction. So let's say we have this point, and I have an acceleration at that point that is this. Right? So that's my acceleration vector. Changing the speed means that I want to go faster along this curve. In other words, I have a tangent vector right here. There's my tangent vector, unit tangent vector, in fact. Which is t. Right, so there's my unit tangent vector. When I change the speed, what I'm doing is I'm changing my acceleration in, well, I'm dealing with my acceleration in the tangent vector direction. So I'd make a projection of my acceleration vector onto, I'm trying to make this a right angle here, right there. So that piece right there, that is the component of the acceleration that goes in the t direction. So if you change your speed, you're changing your component of your acceleration that goes with the curve. So you in tangent to the curve. In other words, and I wrote it right down here, the tangential component of acceleration, the part that goes with the tangent, measures the change of your speed and is the length of the projection of your acceleration vector onto your unit tangent vector, right? So, and then this is the formula for it right here. It's the scalar of that acceleration vector onto that tangent vector. In other words, it's your velocity vector dot product with your acceleration vector and divided by the magnitude of your velocity vector. Right? So looking back here, your acceleration vector is right here. There's a piece of that that is changing speed, and the piece of it that's changing speed is going this way along with the unit tangent vector in that direction along with the curve. So if this is your position right here, this is your position curve right here, then that component of your acceleration, so acceleration is in two pieces. Acceleration has a piece that goes with the curve, right? That acceleration is a change in speed. But it also has a piece that goes normal to the curve. So if you have your normal vector here, sorry, I have to tilt this, I apologize. Right, so let's say that's your unit normal vector. This is really to a very interesting scale. If that's a unit, that means that this is length 1. So unit normal vector n. So I tried to make my pink ones and my green ones the same length because they both have to be unit vectors. I probably wasn't successful, but that's what I was shooting for right there. So those two vectors are both length 1 because they're unit. Okay, so then what's the component of the acceleration that's in that way, and how do you feel it? Well, in this direction, it's the projection back onto this vector. So there's a little right angle right here, just like there was a right angle right there. And this piece right here is the acceleration component in the normal direction. So the normal component of acceleration measures the rate of change in direction. So that's the change in direction. So when you have acceleration, then that's not constant, or even if it is, but constant is just kind of boring. When you have acceleration as a vector, which you do, then there's a component of it that goes with the curve, that's the AT, and there's a component of it that goes normal to the curve, that's AN. This is change in direction, that is change in speed. It is possible to have all of your acceleration in one, all of your acceleration in the other, or more likely some combination thereof. When we're doing one-dimensional motion, like we were in Calc 1 and 2, where you're throwing a rock up and down, then everything is felt with change in speed because there is no change in direction, because there's no direction in Calc 1 and Calc 2, because you didn't have vectors yet, so you weren't capable of doing a change in direction. Now, because we have vectors, we can move through space and have 2 to 3 dimensions, and therefore you can have acceleration as a vector, and therefore it has components in both directions, with the tangent and with the normal. All right, so the normal components formula is right here. It's the scalar of the acceleration vector onto that normal vector. And sorry, there was a typo. That should be AN. I fixed it for future, but if you're looking at this in fall of 19, it will say T there. So fix that to AN. And then that's the magnitude of the cross product of your velocity and acceleration vectors divided by the magnitude of your velocity vector. And so what does this mean for acceleration? Acceleration actually, when it's not a single constant, a single number, has multiple components. It has a piece that goes in the tangent direction. So you take your acceleration vector in your tangent direction times your t vector, plus then it has a component in the a sub n direction, sorry, so a sub n. Right? So there's the accelerational component in the normal direction times your normal vector. These are not dot products. This is a scalar and this is a scalar. So these are scalars and you're multiplying them by vectors to create an overall vector, because the scalar times a vector makes another vector. Scalar times a vector makes another vector. You add the two vectors up and you will have your accelerational vector. Now, in practice, the normal vector, as we've seen in previous lecture videos, is quite difficult to find directly. So we sometimes find n by calculating other values in the equation and then solving for the unknown value of n. So the normal vector can be quite tricky. And we've already seen that. It's a very complicated process to solve for it. So sometimes we'll kind of fudge our way around it by doing other things. But we'll see that in the next video when we do an example of using these accelerational components.